Okay, so I mean, we're talking a lot about this category of functions, but really, one of our main goals is to lay down enough facts that we can basically apply our tools to any kind of system where we have a category of functors from some category C to set. Okay, so I'm going to kind of flip between talking about the general case and then illustrating what this means in the particular case where C is just this category with a arrow from E to V and identity arrows, and in that case we're talking about the category of functions. But in general, if you want to understand this category of functors from C to set, the way to do it is really, in my opinion, to use the Yoneda lemma. You can get so much mileage out of the Yoneda lemma, and it really makes things very kind of visual and arrow centric, and gives you this sort of isomorphism. I mean, I think a lot of category theory really boils down to exploiting different types of isomorphisms at work. You know, the idea, for example, that you can convert between an arrow to A and an arrow to B from a particular object. You can convert from that kind of information to an arrow from the object to the product of A and B, or the idea that you can convert an arrow to its exponential transpose when you're dealing with exponential objects, or the Yoneda lemma idea, which is basically that if you have one of these objects in this category set to the power of C, if you have an object in this category set to the power of C, then if you look at that object, it's basically going to be like a kind of structured set, or like a kind of collection of sets of elements of different types with sort of actions which allow you to convert one to the other. But the idea is that if you have an element of a particular type in such a structured set, like let's say a vertex in a graph or a loop in a bouquet or whatever, the idea is that you can always represent that as a kind of arrow in the category from a particular kind of object. And that kind of object which that arrow emanates from is called a Hom functor. And the idea of a Yoneda lemma is basically that you can talk about all the things to do with objects in terms of such arrows. So it allows you to go to a kind of arrow-centric view. So just to illustrate it very quickly, so you have an idea where we're going with all this, basically in the category of functions, there's two of these Hom functors. There's Hom E comma blank, which turns out to look like this. In fact, it just looks like a terminal object in this case. And there's also another one of these Hom functors called Hom V comma blank, which turns out to just be a single vertex. And then if you have some more kind of complicated, actually I shouldn't have drawn an arrow on that, that's just a loop, okay, because we're talking about bouquets. And if you have some more complicated kind of object, like say this one here, then you can kind of think of that thing as being described by a load of arrows from these Hom functors. For example, arrows from this Hom E comma blank pick out the loops, and arrows from Hom V comma blank pick out the vertices. And then there's also a kind of arrow which we call H to the power of S, which goes like this, and sort of composing, say, this one of these things that injects a loop, composing that with H to the power of S would basically give us this kind of arrow, which is pointing at the kind of vertex of that loop. So this is the basic idea in a nutshell, at least as we're going to apply it to this category of functions. But of course, being the Yoneda lemma, it's much deeper and more general, and we can really use it to understand the fundamentals of lots of things in general categories of functors from C to set. And I know I've already talked about the Yoneeda lemma before. I've done a whole video on it, so this is going to be a bit more brief. I'm just going to get at the sort of three main things that we need to know to be able to use this result to understand all sorts of features of set to the power of c. And even this stuff, I've already discussed it in previous videos, but I just find it difficult to make a video on this kind of topic without sort of going for a quick recap of the Yoneeda lemma, because it's just so integral to you know, what we're doing, and it's like actually easier to like recap the Yoneeda lemma and sort of see how all the results spring from it. It's easier in a way than just sort of trying to memorize the results themselves, because you see how they all kind of come about organically. But on the other hand, there's quite a lot of stuff to the Yoneeda lemma, and so to simply assume that the viewer can remember it all seems a little bit of a tall order. So I think it's worth going through the basic ideas again. So, okay, probably the most important component in the Yoneeda lemma that we still need to introduce is this idea of a Hom functor then. So let's let Hom, so we'll suppose that E and V are objects in our category C, and again we'll work with a general category C, and we let Hom E comma V just denote the set of arrows in C from E to V. Okay, and then Hom E comma blank is a functor from C to set. Okay, so we're just supposing that we've picked a particular object E, we're sort of holding it fixed, and this makes us this functor Hom E comma blank. Now, how does this functor work? Well, the way it works on an object V of category C is that it sends V to Hom E comma V. Okay, so that's how it works on objects. When we operate this functor on an object of C, we just get the set of arrows from E to that object. Okay, and that's obviously going to be a set, so it makes sense. How does this functor work on arrows? Well, let's say we have an arrow F from A to B in our category C. Well, then we want Hom E comma F, the kind of lifting of F under our functor Hom E comma blank. We want that to be a function that goes from Hom E comma A to Hom E comma B. Okay, so this is the kind of picture that you ought to have in your head, okay? Basically, we want to cook up some function which is going to send arrows from E to A to arrows from E to B. And there's an obvious choice sort of indicated by this diagram, which is what we do. And basically what we do is, if we want to operate this function Hom E comma F on an element X of Hom E comma A, in other words, on an arrow X from E to A, then the result we just define to be F after X, because that's going to be an arrow from E to B. Okay, so basically we can say that when we lift an arrow of C under our Hom functor, it just turns into this kind of function which maps the set of arrows from E to A to the set of arrows from E to B in such a way that it just sort of takes an arrow from E to A and then it does F after it. Okay, so I'll leave it to you as an exercise to prove that this sort of Hom E comma blank, as I've just described it, is actually a functor. Okay, hopefully it's clear that the lifted arrows under this functor have the right kind of source and target sets. But then you'd still need to show that this kind of functor, if we lift the identity arrow under it, we get an identity arrow as a result, and also that this functor preserves composition. Okay, but I mean, it's pretty clear that those things are the case. I mean, basically, if f is the identity, then you can see it's not going to. Then you can see that this function here is going to be the identity function, and you can also see that we just end up sort of composing arrows on the left, and we'll have that kind of composable arrow property that we want functors to have. Okay, so these Hom functors are really essential for the Yoneda lemma. They kind of lie right at the heart of the idea. And so let's already go and have a look at what these Hom functors look like in our category of particular interest. So I keep sort of flipping in this video between discussing the general and the specific, and I sort of like to write these red lines here, sort of indicate that I'm flipping from either the general to the specific or vice versa. So now I'm talking about the specific case of the category of functions. So I'm thinking about this category C here, this particular one where we have an arrow S from E to V. And so in this case, what do our Hom functors look like? Well, let's think first about Hom E comma blank. So we're really going to have two Hom functors. We're going to have Hom E comma blank and Hom V comma blank. So we have a Hom functor for every object of C. So let's think about the object E to start with. So we'll think about Hom E comma blank. So how does Hom E comma blank work? Well, it's going to send object E to Hom E comma E, which is the set of arrows from E to E, which is just, in this case, just the set including the identity arrow of E, as we can see from this picture. And also Hom E comma blank is going to send V to Hom E comma V, which is just the set of arrows from E to V, which is just the set which just contains S. Okay? Now, the other thing is what happens to this arrow S. Okay? So Hom E comma blank sends this to Hom E comma S. And so this is going to be a function from Hom E comma E to Hom E comma V. And how does this function work? Well, I've already kind of described it up here. So it's going to send an element X to F after X. So in our case, there's only one element in the source set, which is identity of E. And so it's going to send Hom E comma S is going to send identity E. And so Hom E comma S is going to send identity E to S after identity E, which is of course just going to be S. So this function here is pretty simple. In fact, it would have to be this kind of form because this is the only possible function that we can have from this set to this set. So, okay, this is basically what Hom E comma blank looks like. If we're thinking of this as a function, it's just this function that sends this singleton set here to this singleton set here. But we like to visualize these things as bouquets. So what's this look like as a bouquet? Well, we just have one loop, which is called identity E, and one vertex called S, and the loop goes through the vertex. So this is what Hom E kind of looks like as a bouquet. And I mean, one of the lovely things about these bouquets is it just gives such nice little compact ways of illustrating information. And now we can immediately see that hom e comma blank in this category looks just like the terminal object. Okay, so it's isomorphic to the terminal object, and that's very interesting, and it's going to sort of help us to understand lots of things about this category of functions. So that's one of the hom functors. The other hom functor is the one associated with object V of our category C. So let's work out what that one is too. So now we're interested in hom V comma blank. So this is going to send E to hom V comma E, the set of arrows from V to E. Well, let's just have another look at our category. Well, there are no arrows from V to E. So E just gets sent to the empty set. V gets sent to hom V comma V, which just is the set holding the identity arrow of V. And then, yeah, okay, S gets sent to hom V comma S, but that's just a function from an empty set. So we can really just ignore all that kind of stuff. The important thing really is that hom V comma blank as a bouquet, we can just really think of it as a bouquet with a single vertex called identity V and no loops. Okay, or if you want to think of it as a function, we can think of it as a function which has a target set with a single element but an empty source set, and there's no problem with that. So hom functors are one of the main things which we want to talk about the Yoni dilemma. There's one other kind of important idea, which is a sort of certain natural transformation, which, or a certain kind of natural transformation, which crops up, and we call this h to the power of s.